Good morning, everybody. My name is Francisco Meléndez. I'm a technical expert at the FIWARE Foundation, and today I'm going to present you the webinar FIWARE Introduction to Robotics, how to get context data out of robots. Let's go. Okay, at first, just give you a summary of what we are going to see today. We will first see an introduction to FIWARE, defining key concepts like what is context data, what is a smart solution, how can this context data be used within them, what is FIWARE and how does it help within this ecosystem. We will look at also at the synergies between robotic systems and other smart solutions. And we will provide you with a vision of what a robotic system is and how you can get context data out from or put context data into robotic systems using FIWARE. So, what is context data? Okay, we are approaching a new digital revolution in which everything that can be connected to the internet and can share information will be connected, just for the sake of having a more smart life. This digital life will always gravitate around context data. And this data is aimed at describing what is going on, where, when, and why in our real life situations. Every physical or virtual entity should be modeled to provide or consume context data from this ecosystem. Three questions must be answered by a context entity when it is requested. It must answer who it is, what it is, which is related to what data model it holds, and what is the current state it has, which is usually described as entity attributes and some metadata. That connects with the question, what is a smart solution? How is the context data used in this? So in this type of solutions, maybe you can find different definitions, but we will adhere to this one that says smart solutions gather data from many different sources. Here is highlighted, including but not limited to IoT devices. And then it builds a picture of the real world to process it, analyze it, and implement a decided intelligent or smart behavior, which in some cases, in the case of robotic system, it is crystal clear, it may imply changing a state of the world. And what is FIWARE? Okay, FIWARE is an open source initiative defining a universal set of standards for context data management. It is free, it contains open source technology, it is focused on context data, and it is standard driven. An important point to highlight here is that FIWARE does not emerge as a competitor to existing protocols, transport methods, or domain-specific solutions. It just aims to extend the possibilities of every technology, providing this new interface and interactions based on context data modeling. On the right side of the slide, you can see the reference 5 blocks FIWARE architecture, in which you can see the central component, the core context management component, the Orion context broker, which is the unique element that you need to include in your solution to be powered by FIWARE. You don't need to use components in the 5 blocks. You can build your solution as you want, but you must include your connection with the context broker. FIWARE also contributes a set of FIWARE-ready technologies which can support you in providing your solution with services, ability, and avoiding reinventing the wheel with services that already exist. You can access to this set of technologies using the link to our FIWARE catalog. But FIWARE is not limited to technology. It's also an independent open community that aims at building and maintaining a sustainable ecosystem around public, royalty-free, and implementation-driven platform standards based on context data. It targets at multiple sectors, and the links you see in the screen will guide you through the different ones, like smart cities, smart industry, smart agri-food, and smart energy. Some of our success stories are available here. Let's move on and connect with the topic of today. What is context data? What is a smart solution? And we will see it in an example where we have a food delivery robot that takes a product delivery from a company and takes it to the requested location. Okay, so if we capture this picture of the world, we can translate it in some way to a context data model in which maybe our food delivery robot has its own ID, its type, and the attributes of our food delivery robot can be distinguished between private or secured and public data. Maybe the robot has some customer details, some info about the city, its current location, etc. It can share the company name, the address of the company, or offering some links to the ordering web page, whatever. We can also see in this picture people that usually carry their smartphones, and maybe what we are doing is digitalizing them just as what information or what context data is providing these machines are providing. We can also imagine a smart parking machine that keeps track of their busy slots. They can publish the cost of parking there, etc. What we are doing is turning a real-world picture into context data models. And a second example is putting this data model into a dynamic situation, into a real-world situation where the robot operates. I don't know if you noticed that, but the state of the traffic light is red and the robot is just in the middle of the road. This is a difficult problem if we tackle that with the perception components of the robot. Maybe it needs to check the state of the traffic lights, it can evaluate the group of people over there, or maybe it can track and follow this person in the middle. The perception mechanisms will fit a set of data fusion, deliberative, and executive components, and that will result in a behavior trying to change the state of the robot within this scenario. The problem is that the perception mechanism of the robot will be challenged by many real-world situations. Maybe the light alters the color perception, maybe the traffic light is positioned in a place where the robot is not able to find it, or maybe it is occluded because of another object or because people is in front of the robot. The other point, mimicking the human, does not ensure that the desired robot behavior will occur. We can see it in the picture. So, in this particular case, If we imagine a smart city with smart traffic light systems, a simple data sharing between the robotic platform and the smart traffic light will help us to reduce uncertainty and take this red traffic light as a fact, which will allow the decision mechanisms of the robot to command the desired robot behavior. Please note that maybe this type of reason mechanism is not valid for the green state, because we should be very cautious about ensuring a state that will lead to a risky robot action. In any case, as it is described here, the local onboard robot's decision mechanisms will be the responsible for taking the ultimate decision. Here is a view in which we can see the scenario model as a connection of systems, and we can align that with our view of the current picture of the real-world situation with three entities sharing their data. The point is in that the picture or the black ball integrated in the context broker allows the state of the traffic light and let's say imaginary smart city traffic alert system based on rules to identify that the robot should be helped if it knows that the traffic light turned into a red state. We can also see here that maybe an external solution that does not share context data is also contributing to this application scenario. These connections, maybe they were already existing. It is not necessary to modify them, and they are really contributing through these two smart system applications. Okay, so let's move on to our vision of what a robot is. We can see the robot as a whole system that integrates as a set of planning and control activities. It is able to perceive the world, and in some way it is able to change it. It does it based upon this loop of sensing the world, thinking about it, and making the selective action. That vision exactly connects with this view of our application, in which we are always trying to capture the current state of the world, process this blackboard or picture of the real world, and actuate accordingly. This view, the view we described before, connects with the architectural pattern named as a black box view or system view, in which we deal with the robotic system as a whole, and we need a set of interfaces, a set of modification or a context data model that we can use from this robot. In the middle, you can find a definition of a set of interesting interfaces and states that typical robot use, and our goal is to define them in the standard way we define in the beginning as an entity with an ID, with a type, and a set of attributes. This is the model for a black box view, but in general, robotic systems are too complex. So we need to deal with more structured models in order to get context data out from them or to put context data into them. So this is the typical architectural pattern of robotic systems based on layers. Well, each layer itself can encapsulate a new think, act model. And each layer consumes data at a different level of abstraction. So this view tries to say okay, you can have your robot entity, and within your attribute, you can develop a nested model of layers and isolate each problem and the context data they are sharing. Here is a bit of background about robotics, just if you are entering this world, because we must always be careful of the peculiarities of robotic system. Every layer, in general, integrates perception, planning, and controllabilities. Top layers tend to emphasize on high-level features, on closer to the way humans see the world, and emphasize on planning and semantics of the application scenario, while bottom layers tend to emphasize on control and sensing, perceiving the world through sensors and modifying it through an accurate control of the actuators. It is important to mention that the lowest layer, the one closer to the hardware, integrates a critical control loop where the performance of a purpose-specific robotic software platform is key. We should not try to extract this critical loop from the physical robot platform, taking it to the cloud or to a distributed architecture, because it is extremely risky and it is not acceptable within the robotics world. So what can be useful the standardized context data? Okay, here we propose to monitor robot software platform states, to feed a smart application with the data generated by the robot perception, to deploy, update, and configure this running robotic software, and to increase in general the context awareness of middle and top layers, as we showed in the example. And here I show you a typical implementation of the layer model that divides the robotic system into mission, task, and action levels. In general, the mission level is closer to planning abilities. It cares about allowing the robot to make smart decisions, and it pursues long-term goals. The executive layer overlaps with the critical control loop and focus on control, on ensuring the safety, robustness, and efficiency in the control of robot actuators, and in general deals with sensor reading, actuator commands. Here I connect this view with our example of the food delivery robot, and we can enter into what type of context data model can allow us to connect our robot with the context data ecosystem. And just think about our food delivery robot, and at the mission layer we can think about a mission called product delivery. Then a task within this mission could be the navigation from point A to point B, and within the action set we can find something like path planning, obstacle avoidance, etc. What that means is that in each layer we produce and consume context to support algorithms, a particular configuration space, some system states, and at a high level we are focused on coordination, on task coordination. At the middle level we are focused on tasks, so we are responsible for coordinating action, and at the action level we are dealing with the actuator commands and sensor readings to ensure the convenient robot behavior. So that allows us to enter in a harmonized context data model where all of these features are exposed, and This harmonized environment also connects with the external robot interfaces of the black box system. So here is where we can exploit this context data approach to harmonize multiple robotic systems. Just to include other approaches, you can see here different views. On the left side, a behavior-oriented architectural pattern. On the right side, the component-based architectural pattern. Maybe your platform is closer to these views. In the left side, the behavior coordinator just selects and implements one of the behaviors that are in parallel, and on the right side, we lack of only one coordinator. Every component is responsible of dealing with a task, with an action, with a mission. Everyone can play the role of coordinator or not. So this model is for the less structured platforms, and you can try to adapt these models as I did for the layered model. Okay. So just to recap, at this point we have the set of reference robotic system patterns. We know that we need to standardize our data model, and we already said that data model can be developed as a set of black boxes, layers, behaviors, or very specific components, and we must think about our application loop, how the robot is going to interact with these pictures of the real world and can exploit the information contained in it to to make better decisions. One problem remains here. How do we connect our robotic system with the rest of the ecosystem? We said in the beginning that the only means to do that is to connect it with the Orion context broker. Here, we need to provide you with some reference implementations. Maybe your architectural pattern is implemented within a legacy or proprietary system that you aim to connect with the Orion context broker. Maybe your system integrates robot operating system layer, which is the standard de facto platform for developing robotic software, mainly focused in the academy prototypes, but entering the professional sector. Or maybe you have a pure ROS robotic system, which has two versions, ROS 1 and ROS 2. Or in the last alternative, you have a resource-constrained robotic system, mostly based into microcontrollers, and you want to connect them with the context broker. The alternatives are as follows. If you have your legacy or proprietary robotic system, you may need an IoT agent to access to this information, to expose your data model to the broker and to consume data from it. If you integrate in your robotic system ROS or ROS 2 components, you have specific modules to connect with this with the Orion context broker. In the case of ROS, you have the FIWARE component available, and in the case of ROS 2, you have fast RTPS, which is the middleware standard accepted by the ROS 2 communities. In the last aspect, if you are dealing with a resource-constrained robotic system, which is based on in microcontrollers, you can approach it by using the contributions of micro-ROS, which connects resource-constrained devices with ROS 2 architectures and expose them to the Orion context broker. Here you have the links. If your option or alternative was the legacy or proprietary software, I recommend you to visualize at the FIWARE webinars, the webinars associated with IoT agents. And also you can access here to the information related to the OPC UA agent. If your option involved ROS 1, I recommend you to visit the official site of ROS and also to visit this link to the FireROS component. If you were in the ROS 2 alternative, I provide you also the link to the site and the link to the fast RTPS component. On the other hand, and last, if your alternative was ROS 2 for microcontrollers, you can you also have here the link to access to it. So, in summary, what we have seen today, how to get context data out from or put context data into robot. Here, this slide summarizes your application-oriented view. You have a picture of the real world, translated into a set of context entities, and your goal is to make a smart decision within these real-life situations. So you must know how to capture this picture, how to process it, and make a smart decision to get your goal. You have to take into account which entities are involved to get your goal accomplished, and you can also use this information to exploit smart solutions that already have solutions to part of your problems. Then you have to implement your solution and make it compatible or able to access and provide context to the Orion context project and close this loop. The second view allows you to focus on the robotic system, and maybe you can enter from each one of these 4 aspects. You have your pattern, you have your implementation, and now your problem is to develop your accurate data model and to specify the goals of your loop. Maybe it is the other way around. You have a problem that you want to solve. You must think which pattern is more useful to you, select the technology, and develop your data model. That's given the complexity of robotic systems. Every way of design is, in general, common. Okay, that's all from my side. Thank you, and just connect with us if you need further explanation. Let's see you in a new tutorial.